welcome everyone. We are privileged to have with us here today Dr. Peter Murray-Rust, who is currently a reader in molecular informatics at the University of Cambridge and senior research fellow at Churchill College. Dr. Murray-Rust is the creator of CML, Chemical Markup Language, and is heavily involved in the open data and open access movements. And he will be speaking to us today on the Semantic Chemical Web, GoogleInChI, and other mashups.
Okay, thanks very much indeed, Leslie, and I'm delighted to be here. Just to say that the reason I'm here is that about a month, six weeks ago, you held a Google Foo Camp with Nature and O'Reilly. We've been working very closely with Timo Hannay at Nature in London. Timo was one of the organisers of that, and he invited me, and unfortunately I had a clash. So my colleague Peter Corbett went instead. I'll be showing you some of Peter's work. Really excited to be here because I've been in the sort of information game for 30, 40 years, something like that. I'm a chemist by background, but I really feel the time has come when the world is going to explode with information. So this is a major powerhouse that's driving it, and I'm looking here to ways that we might jointly take this forward. So I've not come with any preconceptions, but I do believe that the combination of Google technology with the stuff that we've been developing in chemistry has got enormous power. I think it can literally change the face of chemical information. I can just introduce here Steve Heller. Steve is from NIST and is the guru of INCHI, and I'll be explaining INCHI in a minute. So anyway, first of all, when I give presentations, I used to give presentations with HTML slides here. I hate PowerPoint for various reasons. It destroys information and it destroys brains. And so I've now, over the last few days, taken to writing a blog. So my slides and my message will increasingly be found on the blog. So if you put Peter Murray-Rust and blog into the web, you'll find it. So one of the things, these are the things I've been interested in here. You can see I'm interested in open data, the idea that there's basic scientific data which belongs to the human race. And that is things like the melting points of compounds, genome data, things of that sort. And that cannot be copyrighted or owned or patented by people. Here, for example, the question of scholarly publishing, and one of the key things I'll be looking at is scholarly publishing. We used to read journals. Now the publishers say you have access to a database. This has changed the way we publish information, I think, for the poorer, because it means that we no longer have that possession of the information that we used to have. And then, not only do I hate PowerPoint, I hate PDF. PDF is one of the greatest destroyers of information developed in the scientific arena. And Mike Kay of XSLT and Saxon came up with this lovely statement down here, if I can find it. Where is it? Oh yes, could you tell me how we convert PDF into XML? Mike says converting PDF to XML is like converting hamburgers into cows. So, you know, for goodness, can we get away from PDF and go to something semantic? So my slides are semantic, and you'll find most of them in the blog. But you'll also find that I give a number of demos here, and those demos are not easy to distribute. We're looking at ways to distribute the demos. But basically, I'll be doing these from bookmarks here and so forth. So the first thing I'm going to do while I'm talking is I'm going to give you a demonstration of JMOL, because this epitomizes much of what I'm going to be talking about. Now, JMOL is the leading molecular visualization tool, along with PyMol. Both of these are open source. And this is not a movie. This is actually a real live scientific application. This is caffeine, and this is being driven by a script. But I can do that. I can move it around, so it's a live, living object. And that's been transmitted from the website into the applet. So we have the power to transmit semantically rich information. And this can be coming down in chemical markup language, so it's fully chemical markup language aware. And as you will see, there are many, many different things it can do. It's computing these pictures on the fly. They're not pre-prepared. It's computed those surfaces within the applet. And the guy who wrote JMOL, Bob Hanson, is an absolute genius. He doesn't have research students because he's at a liberal arts college, St. Olaf in Minnesota, and he does this by himself. And this is one of the great things about the open source movement, that with the internet we can build virtual communities. So when the movie's finished, and I just want you to look at it and say wow, because it is just wonderful. That is the sort of thing that we should be transmitting over the web. And this is the sort of thing also that we should be able to search for. We should be able to query these things in the language that the scientists use them. So those were proteins, and we ought to be able to say, does the protein have a helix in? Here is the well-known double helix of DNA. We might want to say, let's search for all double helical molecules on the web. And that's the way that I want to see scientific information going. That you simply use natural language, put it into Google, and off you go. Now, I believe that chemistry is the best subject almost in the whole world to do that, because it's very well understood. It's been around for 150 years. Chemical information is a mature subject. We know how to do it. And if we get the right protocols, the right semantics, then we can do it. And I'm going to show you that in a minute here. So I think there's a bit more of it. There's lots of fun here, but you can download. You can do this at home. It's safe, right? Okay, and fun. So I'm now going to go on to talk about how we put this together. Now, open source, I'm completely committed to open source, but open source is more or less either a dirty word in chemistry or it's seen as a Mickey Mouse subject. So anybody involved in it is seen as off the wall. You know, what are these guys barking at? If it doesn't cost money, it can't be any good. That's the sort of thing that we have to fight against. And I'll talk a little bit about why I think the economics of this has been distorted by the pharmaceutical industry. I used to work in the pharmaceutical industry, so I can make comments like that. But I think the pharmaceutical industry has created an artificial market for software which actually is now counterproductive. It turned out that there are some heroes here who have developed software, of which JMOL is one, and there are a number of other very competently put together ones. And this has been a real labor of love, because these are built as toolkits. They use modern methods of object-oriented design, of web integratability, and so forth. And at the very end, I'm going to show you something called BioClips. But basically, 2 years ago at the American Chemical Society meeting, we got together under the Blue Obelisk in Horton Plaza, San Diego, and went out for a meal. So that was how the Blue Obelisk was born. Now, it was a little bit of fun then, but now we believe that, in fact, people are starting to take us seriously. So we had a meeting last night, and we had the Blue Obelisk Awards. They went to Christoph Steinbeck, who developed CDK, and Jeff Hutchison, who developed OpenBabel. When I say developed, they are the current gurus of this. There's a sort of guru successorship in this, which passes down. So they are responsible for that. These are real labors of love, because building toolkits at the best of times isn't fun. There's blood on the floor at midnight, as I call it. And they've done it with, I would say, a mixture of apathy and antagonism from the community. So, what do we now have? Right. I'm going to show you, you will know all about mashups and so on, but I just wanted to show you a very simple mashup, but a very exciting one, which is nothing to do with chemistry, which was done by some geeks that we meet with in Cambridge. And these people want to liberate local information. So they built this mashup. Having said that, oh, wait a minute, I know what the problem is. Yeah, the problem is that when I got to the ACS meeting, I said, could I have an internet connection? They said yes. And when I turned up on the day, well, they said, well, no, you couldn't. We can't manage an internet connection. This was in San Francisco, which you would have thought knew about the internet, but it didn't. So I had to sort of put all my slides on HTML. So I just wanted to show you this. It's a very simple mashup. Google Maps here mashed onto Wikipedia, so that if you go to one of these, and I've no idea what it is, it uses the Google API to get the Google map, and it uses the Wikipedia API to go into the article, and so you can find anywhere in the world what are the Wikipedia articles of interest in that area. That, I think, is a really very clever idea, and the developer said that he would be offended if I said it took more than 3 days to develop. So what you've got is something which is mashed on top of 2 different data sources. And I'm going to show you that with GoogleInChI, which I think does exactly the same sort of thing. Google doesn't know that we're doing GoogleInChI. Well, it does now, obviously, because I'm telling you that, right? And PubChem doesn't know we're doing GoogleInChI, but both of those we access through their APIs. Right, so just before I do that, I'm just going to say a little techie stuff. Are you happy for a little bit of techie stuff? Right, okay. Right, so one of the problems we have, somebody actually got up at the meeting and said, look, in chemical informatics, we have all these different programs. They don't speak to each other, but there's nothing we can do about it. This was one of either the pharma companies or MDL or somebody like that. I mean, really, we've got all this appalling mess of non-interoperating programs, and we're just going to accept it because that's the way God designed information. So what we have is that if we try and do anything in chemical information, we end up with a human having to cut and paste or type up or redraw or something at every stage in the process. And it's about time it stopped. So I and Henry Jepper, I'll show you Henry because he exists, and Henry and I are symbiotes, so I'll go to Wikipedia for him because Henry's got a Wikipedia entry, so here he comes, somewhere or other. Yeah, picture of Henry. There's Henry, right, professor at Imperial College, and he put me into Wikipedia as well, so we're both in there, and that's the way we can communicate with people. So Chemical Markup Language does all the mainstream parts of chemistry: molecules, reactions, computational chemistry, spectra, and crystallography. So it's a sort of 80% solution for chemistry. We've been at it about 11 years, and the chemists have not yet taken it seriously. Everybody outside chemistry believes it's an established fact. So that's, but that is changing. It is beginning to get taken seriously in chemistry. It's the only game in town anyway. We first of all developed it as a sort of object-oriented architecture, and the idea was to use XML schema for inheritance. But I think XML schema is one of the most awful things designed, and it has convinced me that the way forward is ultra-lightweight information design. So we use XSL schema for the data types, but we don't use it for any sort of inheritance. So CML consists of something that looks like this. So there's a whole lot of different things here. Each of these are XML elements in the schema. And how many of you have done some chemistry in your life? One. Okay? Right. Well, you might... I mean, these are not too hairy, are they? I mean, they're ordinary names that mean something, okay? And what you'll see is that this lot is chemistry. But this lot over here is general physical science. So what we've had to do is actually invent a language not just for chemistry, but for physical science in general. And that is a key part of CML. It is actually very easily adaptable to a whole range of physics and engineering and other STM areas. And we're, of course, very happy to share it with people. And the key technology that we use is a very lightweight dictionary. So if we have something like the compound melted at such and so, you don't develop a markup element called compound or melting point or whatever. You use a generic tool here, scalar. It has a data type, which in this case is an XSD float, and then it links to two things. It links here to a dictionary, which tells you that it's a melting point, and it will give you a definition in there, and it will link to a units dictionary. So one of the key things is this idea of separating the primary markup into links to dictionaries. And I think this is the scientific equivalent of microformats. One of the great things is anybody can make this up, and it doesn't break it, because the dictionaries are all namespaced. So we would expect, you know, hundreds of dictionaries in science, but we would expect them to start annealing. We would expect authority to say, well, this is a dictionary you should point to, and gradually you would end up with a consensus in the community of the dictionaries that you should be using. Is the volume of this right at the back? Good, okay. Right, so we then see that we can actually build the whole process of workflow in science and in chemistry on XML, and we've done this. So we're able to take things at the left-hand side, which might come out of a database, or they might have been typed up, or they might come out of a journal, and they go into programs, and they get repurposed, and ultimately they end up in databases. And we've done this on the scale of having run 1 million separate jobs using this technology, and all right, some of them crashed, but nevertheless, we're running at, I would say, a sort of 0.1% failure rate, something of that sort. It has to be brought down, but basically you can automate this process, whereas most chemists are still cutting and pasting as they go through this sort of process. So the sort of thing that we're looking at then is, where do we get the data from? So what comes in on the left-hand side, and where do we put it to at the end? Because one of the key things is that in most science, there's a lack of data that you can feed into this. I'm competing against something. Am I winning? Right, so where does this come from? Well, there are, you can say, okay, work on data in chemistry, but the problem with data in chemistry is that you can't get hold of it. It belongs to somebody, and they won't let you have it. Oh, don't worry, Leslie, I can shout them down. Come on, yeah, it doesn't worry me, not unless they start competing. In data, in chemistry, the tradition has been somebody owns the data. If you want to know the ID of aspirin, you have to pay Chemical Abstracts $2. So for every compound you want to know what it is, you have to pay Chemical Abstracts $2. Well, you can get an institutional deal, but since you'll be looking at a lot of compounds, it will cost you an awful lot. And my feeling is that the formula of caffeine should be free to the whole world. It's been around long enough. So we have a problem with the data, so part of what we're trying to do is liberate the data. The other thing is that we get this data in publication. So the primary place that scientific data arrives from is scientific publications. Now, in some subjects, like, let us say, geophysics or astronomy, you often get a database as part of the publication. So they'll go out and look at parts of the sky, and they come back and put all of that in a database. But in chemistry, when people make molecules, they do it on a piecewise basis, so that what you get is what I call micro-publication. Let me see if I've got that in here somewhere or other. I thought I'd put it in. Yeah, here we are. So what actually happens is, here's the chemists, and they're making compounds, and they send them off to a publisher, and these ones send it off to another publisher, and each set of compounds goes into a different publication. And there are probably at least 1 million compounds published a year, and there's no coordination between the publication of these at all, although the general principles are extremely similar, and they've been known for 100 years. So making a compound is like cooking a cake. You have a recipe. We took so much of X, we mixed them together, boiled them, and out came this compound, and we knew what it was because we knew what its color was and its melting point and its spectra. So there are literally hundreds of thousands of papers like that each year, but no coordination. So up until recently, what we've had is we've had organizations called abstractors who've been typing all this lot up again. So there's a big industry in Columbus, Ohio, in retyping the chemical literature into chemical abstracts, and the same in Beilstein in Germany, where they also retype it on a competitive basis. So in my view, this is not a sensible use of human resources. So imagine if we could, when we published a paper, we could actually publish it directly into a database. Now, we've got to tell people that there's a chemical in it, and that's where the INCHI starts to come in. So we will show you now how the INCHI works. Now, imagine also that these papers were actually freely accessible. They're not at the moment because most of these are closed access, but if they were freely accessible, then you wouldn't even need a database. All you would need is a search engine like Google, and you would say, find me all the caffeine, and it would go and find you the caffeine. So what we're now going to do is show how the INCHI makes that possible. So, web GoogleInChI. Right. You joke. No. If that's not available, I'll kill them. That looks to be a problem at our end. Let me just... Right. Okay, well, we'll come back to that later, but that is what I have got, however, and this, I'm afraid, does detract from the magic, but we do have it. We do have, we've copied it somewhere or other, but it is a pale imitation. So basically, here's a molecule. Now, chemists can draw that molecule in different ways, and that's perfectly allowed. There are different reasons for that, which we won't go into, but all of those are actually the same molecule. They're different styles of drawing it. They emphasize different parts of the molecule. And what the INCHI does is to say, no matter how you draw it, there is a single string here at the bottom, which represents the fundamental canonicalization of that molecule. So that this molecule generates that string, and that INCHI string, which is overseen by the International Union of Pure and Applied Chemistry, and that's what Steve is involved in, right? So Steve's responsible for this, and that was published about 12 months ago, and I would say this has got enough momentum in the community that it's now unstoppable. Not everybody likes the idea because you can see it impacts on the business of the secondary aggregators. So I'm going to show you what you would have seen. You would have seen a chemist you'd have seen a chemist draw a molecule like that. Now, I'll explain what happens. This is a normal drawing package for a chemical, and it may be that our server comes back again, although it's the middle of the night, so I'm a little bit worried. The chemist would draw that, and it would generate the INCHI on our server. So now you've got an INCHI string. Now, what the server does is then shoots that off to the Google API. Now, Google does not know it's a chemical. It doesn't know anything. It simply says, here are some characters. Please see if you've got them in your index. So Google then comes back with these characters and says, I found them in the following pages, and we know that they relate to that compound. So I've got a little example here, and So we drew a molecule like that, sent it off to Google, and within a second it came back and it found the hits in our database, because Google had indexed that. I'm going to have one more try, just in case it was a temporary glitch. Otherwise, I will continue on. No, and right. So this is really a pity because, I mean, I can explain it, and I have explained it, but it's valuable to show it actually working. But what you have to accept is that there is no chemistry involved at the Google end, and all that one is doing is turning this into this string, sending it off to Google. Now, the reason it is pre-indexed is because the service at the other end understands INCHI, thinks INCHI is a good idea, and has said, I'm going to add INCHIs to our data. So what I'm now going to show you is a resource that does that. And this resource is called PubChem. And it was started just over a year ago, and it is part of the NIH's Molecular Libraries Roadmap. So here it is, a database of chemical molecules and so forth. The American Chemical Society have tried to get the US Congress to restrict the operation because they claim it competes with Chemical Abstract Service. So you can see the tension here. What we're going to do is we're now going to go to PubChem. The link should be given at the bottom, PubChem homepage, and then we're going to search for it. So we'll search for a molecule, we'll search for caffeine. Oh, I think I mistyped it. Right, so here's caffeine, and if you click on this entry here, it comes up larger. There's caffeine, and you can see there are lots of exciting links from caffeine. So what you're starting to get here is a resource which is part of the whole hyperdomain of bioscience here. And there's lots of information on it, and then down here, towards the bottom, you'll see the INCHI here. So there's the INCHI for caffeine, and that would have been indexed by Google if the Google index had got here. I think it doesn't, and that's one thing I want to talk to you about, because this is a CGI. Does Google index CGIs, or does it skip them? Okay, don't worry. Right, so we believe it probably isn't indexed, but if it was indexed, then the system would find that. Okay, so I now want to move on, having talked about that, to how we can look at journals. Now, journals in chemistry, as I say, do not allow you to read or index their content without a subscription. But what I'm showing here is the ability to read the data associated with the journal. So some of the journals will publish the data, and that data is freely accessible. And what you're seeing here is completely constructed by a robot reading a journal and taking all the data out of it and adding the value to that journal. So this journal consists of several hundred crystal structures, and none of this information, as portrayed here, was actually in the original data file. It's all been transformed and so forth. So here is a molecule, and here you can see the JMOL of it, and if you're a chemist, you'll know that the green ones are chlorines, and you can see down here there are some chlorines, so they are the same molecule, but one's in 3 dimensions and one's the traditional chemical formula. And as we go through, you can see them here. And moreover, if you want to know more about that, you can link back to the original journal article here, which should come up in a minute. Never give live demos, they say, but I think on the web you have to accept that it's worth it. All right, well, let it... But we've also got a summary page for this. So what we've done here is we've created a summary page which is a greater and more powerful resource than was originally present in the journal article. So this is a lot of this is our annotation, and you can see here the robot has actually been checking on the data in the structure here, and the robot has also been able to draw pictures which are not present in the original publication. And as always, you can see the INCHI at the bottom so that any indexing engine can get hold of our data here and index it. There are a lot of... oh my, I've killed the browser, haven't I? I'm sorry. Not very clever. Oh, bring it up again. I have many more things on this demo than I can show you at the moment, and I'm trying to think what is the best thing to show you. I think I'm going to show you the what we call the journal eating robot. So we'll start that one, and that one should start a local server, I hope, and then we are going to carry out a demo on it. Maybe, I think it may need starting manually, so forgive me if yes, it needed starting manually. Right, so what we're going to do here is we're going to see a paper. Now imagine that this paper was freely available on the web, and it's only a political question that it isn't. So this is a paper describing some chemistry. And what we have here is we have... you don't need to understand all the words. All you have to... The take-home message is it's stuffed full of chemistry. Let me... Right, so you can see chemical names in there, and what the robot has done is it's gone through the paper and it's found all the things it thinks are chemistry. So it says, I think 4-bromobenzaldehyde is a chemical name. Now, if you then click on it, the robot will actually work out on the fly what that is. So it will take the benz, which is the thing in the middle here. It will take the brome, which is on the 4 position, and the aldehyde is on the 1 position, and it will work that out. So what you have is the chemists talk in terms of text, but the robot is able to interpret that. Now, it's not 100% because some of these names are so complicated, but you can see here that's quite a complicated name there. Now, what we can also do, and this is where the next mashup comes in, that somewhere in here I've got a word called formazan. Okay, we want to know, formazan is a chemical, what is it? Well, we don't know what it is, but what we can do is we can search PubChem for the formazan. So we go off to PubChem, and it will bring up the PubChem page, and it will tell us that is formazan. So you've got a mashup here in that the original paper does not know we're looking at it because we're superimposing this text analysis on top of it, and PubChem doesn't know that we are requesting that from them. So we're linking the paper to PubChem. And now what we can do, not on my machine but in general, is we can click on that and we can put the entry for formazan, which Oscar didn't know. We can now say to Oscar, this is formazan, put it in your dictionary, so next time it will know that and doesn't have to be asked. And this is really a question of social computing. So what you're getting is that, that if enough people around the world do this, and if they all point at the same server, then they will without any effort, build up a communal terminological resource for chemistry. Right. So Leslie said 45 minutes. I started at 10 past, so I'll spend a few more minutes because I really want to show what I think is the next generation of scientific client. So I'm now going to show you something called bioclips. Since any demonstration is suspect, give me a little bit of leeway when it decides it's just going to have some fun with me. But you know of the Eclipse platform. Eclipse, right. So that is a development environment which has been developed by IBM and put into open source. And what a group of the Blue Obelisk people have done is to turn that into a rich client. So this is using the Eclipse framework, but what we've got here is completely transformed into a scientifically aware system. So I've just got to remind myself where to go. I hope it says sample data somewhere under PMR, because otherwise I'll have a very slight problem. Sample data, and that is some examples here. So you don't have to remember very much chemistry, but do you know what a spectrum is? Right, okay. So this recognizes that this thing here is a spectrum. And when you click on it, then it actually says this seems to contain a spectrum. Should the spectrum perspective be opened? Yes? Thank you, Bioclips. And so it comes up. And down here, it says, well, I understand this spectrum as a so-called continuous spectrum, and I can magnify it, and you can see that these peaks are actually, you know, real peaks like that, and so forth. So this is a living plugin. It's called JSpecView. It's written by the leading open source developer. He contracted this to Molecular Design for several years, but he's now got that. He's managed to take the IPR out of Molecular Design, so it's now fully open source. So we are beginning to do those sort of things. Similarly, if I do the other spectrum, it's what's called a bar spectrum, a mass spec, and here the peak list correspond to the peaks here. So if I went to say peak 29, watch that one very closely. I go to peak 29 and I say delete, and it disappears there. Now, that's not a very good thing for graduate students to be allowed to do because they might be editing their data. But we have a completely live spectral viewer here. Similarly, we can go down to the molecules. So here's ATP. This appears to contain a molecule. Shall we show it? Yes, so here's ATP. And this is a live thing. You can see all the edit buttons over the top. So if I click on that, let's see, can I draw? Yeah, I can draw on that. So I can edit the molecule here. We have a live chemical editor. And that, again, is a Blue Obelisk product. And finally, here's Viagra. We put that one on, and we got a 3D molecule in there. And so we're creating plugins for This is Bioclips, Leslie, open source, rich client. We have plugins for all the major chemical functionalities in that. And perhaps the most exciting one, which I hope will work if I'm lucky, is RSS. Now, RSS, this might fail because I think our server is down. But this has developed something called CML RSS. So it actually sends not text in the RSS feed, it sends real molecules. And this thing is able to understand these things as molecules. As I say, it will probably fail unless our server is up again. But that is a feed of all of these molecules, and if, and I think it is an if, no, it doesn't seem to be, it seems to be a problem at the moment. That ought to be an RSS feed coming off our server with these molecules. So 51, I've been talking for 41 minutes. So just to summarize, we have a number of issues here. We have technology which we would like to be able to distribute. BioClips is an example of that. If there was a way of getting BioClips onto the average chemist desktop, then we would have solved things. We are not probably strong enough as a community to make that happen because chemists are very conservative. How do we develop this client to the stage where it sells itself and so forth? So that's one of our questions. The second is that we have to break this problem of the flow of wealth. So here is what I drew as the flow of wealth in the chemical software industry. And the problem is that pharma contracts with these software companies who are closed and database companies who are closed and pays them a lot of money, and they supply products into the pharma industry. But none of these effectively come back to the community. So the flow of wealth is from the scientific community down to the service companies. I'll be generous, the service companies for the pharma industry. Now this is a large market. I don't know what I would estimate, but I mean, if we said $1 billion a year, that would probably be an underestimate, wouldn't it? I think so. So you know, in our terms, it's a large market, and it fuels, 20 different software companies. They're all competing against each other. They all have very similar products, and the products are based on technology which is 10 years old at least. So none of them use web technology in the way that it's meant to be at the moment. They don't have plug-in components. They don't use lightweight services, semantic web. They're not developing ontologies. They're not using XML. It's not for exchange of content. So you have something here which I'd rather not show you. And here you've got the scientists who are trying to do it properly, who are trying to work with their neighboring disciplines, but because of this, it's very, very difficult for us to be taken seriously. They can put the resources in, they've got the people in the suits who go and sell it, and also they can stand up at meetings and say, oh, well, we have the best text parsing, text mining system in the chemical world. We've solved it. Well, you say to them, well, what's it do? They say, oh, well, we can't tell you, it's a confidential secret, but it's the best in the world. And that actually makes it very difficult for us to develop things. We publish in peer-reviewed papers, they don't, but they have the power to sell it into the industry. So it actually makes it very, very difficult to get the modern technologies taken seriously in the industry. So I will finish there and just go back to my blog where I have one of these in my presentation, as is under here, but these are some of the people that I want to recognize. So we have people in the blue obelisk. We've got at least 2 people from last night who aren't on this list. We have Warren Delano, who's PyMol, and we've got Jimmy Stewart, who has donated Mopac, one of the great computational programs, into the public domain, or into open source. Then there's Henry Zepper, my symbiote, and then there are people at Cambridge. Now, one of the exciting things here is most of those people are undergraduate students, and the system you saw, the Oscar system, was really built primarily by students. I haven't shown the data-eating robot, which can go to the literature and actually suck data out with a very high percentage. And the undergraduates do very well because they haven't been institutionalized. And then we do have funding from a number of people here. We couldn't have done this without funding, but a lot of this is marginal on other projects. It's not easy to get funding precisely for that sort of thing. So that's me. Again, I'd like to thank Steve very much for his pioneering work on INCHI, because I think that's the one most prominent thing that will make this fly. People can understand it. I will just go back and see if it works, but I'm not optimistic. And I will talk very severely to our server when I get back. No, it's not there. And again, this is one of the things we want to do, is we actually want to get self-replicating services. So we would like mirrors of these services. And again, one of the things that we want to do is to be able to package these services up so that anybody can take them and install them easily. But creating distributable packaged services is not easy, and again, that's something I like to pick your brains on. So, there we are. Yes.
So is INCHI, is that like a...
Yes?
How are INCHI and Smiles related?
Right. Smiles and INCHI have the same basic philosophy, which is that you take a molecule. I'll go back to the molecule if I can find it. Put that one away. Let me just see if I can find this. Right. The first thing you have to do when you read the molecule in is to normalize it. So it takes all these molecules here and normalizes them to the same internal structure. It then has to canonicalize them, so it works out a unique numbering scheme for that, and then it has to serialize it. Now, in principle, the first two bits are the same in any language, but the details differ. We don't know what it is in Smiles because the code is closed, though we can guess it from the outcome. INCHI is a somewhat more elaborate and slightly more verbose language than Smiles, but it's basically the same. This says 6 carbons here, and then carbon 1 is joined to carbon 4 to carbon 6 to oxygen 8 and so on, and then these are the hydrogens here. So INCHI is very similar to Smiles. You can translate between them one way and the other, but INCHI is developed so that it can deal with more complicated molecules, including transition metals and so forth.
They're both linear notations, effectively, but Smiles is proprietary, and over the years has had various versions, and so there's a great deal of incompatibility. This is an open source public domain version, and it also covers a larger class of chemistry. Smiles was developed primarily for the pharmaceutical industry, and as such only covers primarily that area of chemistry. Which INCHI or well, yeah, it hands it's ferrocene and organometallics and so on. We're going to start extending it to polymers, for example, which is something that Smiles doesn't care about because it's a business-oriented notation, and it's done very well because the pharma industry has done very well over the years. But that's to be honest with you, the primary difference of the two of them. And this is being extended and adopted by the government. It's becoming an international standard through this International Union of Pure and Applied Chemistry. So it's been institutionalized in a much more public and open way. It's going to be here in 10 or 20 years for sure. Whereas the other one, you don't know if it's going to be here and what version is going to be here.
What would you like to see Google do for bioscience?
Right, well, I think Google is doing a lot for the bio bit, so let's say for the chemistry, right? Well, I'll throw some ideas out and see if any of them make sense. The first is that I think it would be very nice to have somebody or some group here that we could be in contact with and discuss things. So that, that would be the first thing. The second would be that Google was able to say, this is something that we, Google, take seriously at some level, and we're exploring how best to look at indexing or representing chemistry on the web and so on. To say, this is something which can be done properly, and we're playing our part in doing it. So if we take those and then move on, I would say that you then come to looking at aspects of the technology. Now, the indexing of INCHI by Google is generally, from our point of view, a bit of a mystery, and when we started this, we actually found 100% recall and 100% precision. We put 100 inches up on the web, and Google indexed all of them, and when we searched for them, we got back only those 100 and nothing else, which is a remarkable thing. So it is really very, very powerful, whereas if you use Smiles or Cass or something, you get back football scores and Crazy Frog and goodness knows what, right? So it is a very precise technology. On the other hand, it's got some problems with the syntax here, in that we're not quite sure, but we believe at the moment that you have to take the INCHI equals off or something like that for it to work. You know, we have a little bit of folklore because we don't know what's going on at your end and so forth. And we have mailed people. We also feel that some of these things sometimes drop out of the index, or that we can no longer find them when they used to be there. And so there's a general feeling that we don't quite know what we're looking at and dealing with. I think probably also, if one could get to the stage where certain data resources were indexed by INCHI, even though Google might not index the CGI. I mean, if you go to PubChem, we would like the INCHIs in PubChem indexed, even though Google will probably skip them at the moment because it says they're a database, something of that sort. It's so important to us to be able to get that, to know that if you put an INCHI on the web, you can guarantee getting the PubChem index for it. And there will be other resources like that. So we'd like to be able to say to people, this is the guaranteed way of getting your INCHIs indexed by Google. Then I think there would be some general support for easy generation of INCHI. Now we have the technology, but it's useful if we can say, well, Google and NIST and Cambridge agree on the best INCHI tools to use, or this is the current version of INCHI tools, don't use the other lot, and so on. So that's, you know, we're not looking at major version control, but versions and things can be a problem. I think you can. So does that all make sense so far?
Well, in answer to your last question, the way to get INCHIs into Google is to use Google Base. And you can connect them to PubMed using Google Base. You should take a look at Google Base. It's a relatively new thing.
Fantastic. That sounds very exciting.
Another alternative also is to get a really good sitemap file up for it, so we know where to find things.
We want you to tell us the best thing to do, and to agree on a protocol that we can both say this is the best way of doing something, and that would be a major step forward, wouldn't it, Steve?
I get, you know, Peter and I are not exactly twins, so.
I guess, you know, my comment on you know, what to do or what's going on is, first of all, the question I had, and Peter and I were talking about on the train down here, you know, does Google really care about chemistry? You know, is there an interest in doing something? Or is it just, you know, random kind of things? Well, let's do this in science or do that in science. And you know, if that's the case, you know, is there someone here at Google that we can communicate with on a regular basis to try to develop and see what can be done that would benefit the chemical community as well as Google? Obviously, the INCHI is one possibility, and we'd like to be sure, for example, that you don't cut off parts of the INCHI, that we can put a string in, that the pluses, the minuses, the parentheses don't disappear as they might normally disappear for other things. Is there a way of doing that? Is it worth doing it? And so forth. And, you know, not knowing anything about what's going on, not being able to talk to anybody because we don't know what's going on, obviously makes it very difficult for us to think of anything to do. And I think, you know, we're very much interested in open source, open access, open data, and the things that are available, that if Google can enhance those through Google Scholar or whatever these other things are, as I'm sure you probably know, there was a lawsuit against Google by the American Chemical Society for just the name Scholar, which they lost, and that's been settled. But, you know, we'd like to know was anybody technically involved? Forget the lawyers and you know, the technical people who caused the lawsuit. You know, who are they? Do they ever want to talk to anybody on the outside, or is this a self-centered operation that does whatever they want and doesn't really interact with possible people in the community? If there's somebody who cares, I'd like to know who he is or she is to possibly communicate and see, you know, if there's something interesting that we might be able to do on a random basis or on a regular basis. But, you know, up until today, I had no idea about anything about Google other than I use it all the time.
And does that make sense at this level? You know, I mean,
Oh, yeah.
Yeah.
Perfect sense.
And obviously, there may be ways of, larger scale collaborations in the future and so on, but we're not coming here, with any preconceptions of that sort of thing at all. It's finding out what's possible. I mean, I think I would also say to Leslie that we are also particularly keen in what Google might wish to do in promoting open source and supporting the sort of activity that we have and perhaps advising on ways forward and so on. But and that of course
Well, we're good for that.
Yeah, and actually we need to take you to lunch now, so let's talk about it over lunch.
Okay.